Okay, moving on to question 6 of the halogen derivative tutorial. We are looking at a chemical test or rate of hydrolysis question. So we have bromoacetonephenone. Okay, so if you look at this compound, this Br is attached to a sp3 carbon. It's your halogenoalkane. If you look at the question context, they were treated separately with boiling aqueous potassium hydroxide. So recall, aqueous potassium hydroxide, heat, you're doing your nucleophilic sub. Your OH minus is the nucleophile. So basically the Br will be replaced with OH minus. Alright, the Br will be replaced with OH minus. Br will be replaced with OH, and then you kick out Br minus, which will then use your silver nitrate to test for it, and you get your different AgBr, AgCl kind of PPT. Okay, so you can take a look at the context of the question. We have chlorobenzene, bromoacetonephenone, chloroacetonephenone. These two are essentially the same class of compound, halogenoalkane. And we have this compound. Okay, and you have different observation. Now, for chlorobenzene, there's no PPT form. Why? Because we know it's a halogenoarene. Again, in this case, the Br atom is bonded directly to a C. So it's a halogenoalkene, and that's why you see the PPT forms very slowly. In the case of bromoacetonephenone and chloroacetonephenone, they are both halogenoalkanes, as I have mentioned earlier on, and that's why the PPT forms quite readily. Okay, but you can see the bromoacetonephenone forms quite fast compared to the chloroacetonephenone. So there are, in terms, three things you need to explain why one halogenoarene cannot undergo nucleophilic sub, alright, with potassium hydroxide, why halogenoalkane undergoes nucleophilic sub but very slowly, and why is there a difference in reactivity between bromoacetonephenone and chloroacetonephenone. So three components: one for halogenoarene, one for halogenoalkane, and the comparison between bromo and chloroacetonephenone. Okay, so let's take a look. So explain why chlorobenzene does not form PPT. This is standard. We explain this. This is standard bookwork. Your lone pair of electrons on the chlorine atom is delocalized into the benzene ring. So this strengthens the Cl bond in chlorobenzene due to the presence of partial double bond character, and therefore nucleophilic substitution is impossible under normal condition. Okay, so you can see no PPT forms. Okay, for halogenoalkane, it's going to be very similar, so let's explain this first. In halogenoalkane, we explained this earlier in question 4, the lone pair of electrons is delocalized with the adjacent CC double bond. This strengthens the CBr bond due to the presence of partial double bond character, so you can see the phrasing is very similar. It's just that this is delocalized in the benzene ring, this is delocalized into the CC double bond. Okay, but it strengthens the bond, CX bond, and due to partial double bond character. Okay, and therefore nucleophilic substitution, in this case, to answer to the context of the question, I do not say it's impossible, I just use the word difficult. Why difficult? Because eventually it still happened after 70 minutes, after a prolonged period of time. Okay, to compare between bromo and chloroacetonephenone, why is there a difference in reactivity? This is the standard bookwork. Your CBr bond is weaker than your CCl bond. Alright, how do we know that? Because bond energy data says so. CBr bond has lower bond energy than CCl, which means the CBr bond is easier to break than CCl bond, and as a result, your bromoacetonephenone will be more reactive than your chloroacetonephenone. Okay, so this is how you organize your answer so that you won't miss out on any part. One for your halogenoarene, one for your halogenoalkane, and one to compare between the bromo and chloroalkane. Okay? Question 6, done.